Yellowstone Supervolcano, diverse chemistry of the hydrothermal features. This is the latest of Caldera Chronicles, December 16, a weekly column written by scientists and collaborators of Yellowstone Volcano Observatory. And this week's contribution is from Blaine McCleskey, research chemist with the U.S. Geological Survey. Yellowstone National Park contains more than 10,000 hydrothermal features, including geysers, hot springs, mud pots, fumaroles, and steam vents. These hydrothermal features are beautiful, interesting, and unique because of their variable sizes, colors, activities, microbial mats, and temperatures. But have you ever thought about the chemical composition of these features, or how water chemistry affects the color, the microbial communities, and physical features of the pools? Why do some pools have large siliceous sinter cones, or colorful microbial mats, or travertine terraces? The answer to the questions are often tied to the chemistry of the hydrothermal waters. Thermal waters at Yellowstone have pH values ranging from less than 1 up to 10. Surface temperatures as high as 93 degrees Celsius, which is boiling at Yellowstone's altitude. Some pools are even superheated and often have high concentrations of chloride, sodium, silica, hydrogen sulfide, sulfate, alkalinity, and arsenic relative to many natural waters. And we also know, it's not mentioned here, but they contain a very high degree of mercury as well. Now, investigations into the water chemistry of Yellowstone's geysers, hotspots, and mud pots, and streams and rivers have been conducted by the U.S. Geological Survey dating back to 1888. The classic 1935 Carnegie Institution report, Hot Springs of the Yellowstone National Park by Eugene Allen and Arthur Day, is an exhaustive compilation of water chemistry and wonderful physical descriptions of hydrothermal features and surrounding geology. Modern chemical studies of thermal waters not only focus on the major chemical composition, but often include studies of gases, carbon dioxide, hydrogen, hydrogen sulfide, nitrogen, and argon, isotopes of oxygen, hydrogen, sulfur, strontium, and mercury, redox species, sulfur, arsenic, and iron, and trace metals including mercury and the rare earth elements. These modern studies aim to provide insight into the underground hydrothermal plumbing system, formation of minerals, microbial processes in extreme environments, and the fate of chemicals as they emerge and are discharged from the thermal features. Yellowstone hydrothermal waters have been grouped into a few main categories by several researchers, and for more details we can see Fournier Geochemistry and Dynamics of Yellowstone National Park System. But it's important to recognize that most of the surface water in Yellowstone is meteoric, that is, it's derived from snow and rain. Consequently, many of the hydrothermal waters in Yellowstone are mixtures of meteoric water and either hydrothermal fluids or gases. Also, some of the various types of thermal waters mix. Besides mixing, the chemical composition of thermal waters is affected by many processes, including fluid-rock interactions, boiling, and subsequent separation of liquid and gas as phase separation, mineral precipitation, and microbial activity. In short, Yellowstone thermal waters are very complex mixtures. The first type of hydrothermal water, often called neutral chloride, is a deep, high-temperature water that often interacts with volcanic rocks on the way to the surface. And at the surface, neutral chloride springs often discharge significant quantities of water containing relatively high concentrations of carbonate, chloride, silica, and even arsenic. These waters are common in Yellowstone's famous geyser basins, the upper, the midway, the lower, West Thumb, and Norris, and often have silica sinter deposits, some of which have accumulated into large amounts in cones like Old Faithful geyser. A second type of thermal water, often called acid sulfate, is meteoric water that has been infused with high-temperature geothermal gases, carbon dioxide and hydrogen sulfide. These waters tend to be low pH, less than 4, contain high sulfate concentrations from the oxidation of hydrogen sulfide, and have low chloride concentrations. Some acid sulfide waters contain elevated concentrations of ammonium and mercury. These features tend to be fumaroles, mud pots, or acid sulfate boiling pools with little to no discharge. The landscape surrounding these features is frequently barren and composed primarily of clays and resilient quartz minerals, and these waters are common in features in the mud volcano area. A third type of thermal water flows to the surface through sedimentary rocks, preliminary limestone and gypsum-bearing shales, and is enriched in sulfate and bicarbonate. These waters tend to have lower reservoir temperatures and have relatively high concentrations of calcium and magnesium, but lower silica concentrations. And as a result, the waters often form travertine deposits and are commonly found in the Mammoth and Snake River hot springs. We still have a lot to learn about the behavior of Yellowstone's hydrothermal systems, but we can gain insight about the subsurface by studying the chemistry of thermal features and monitoring their changes over time. And also, in conclusion, I'd like to remind everybody that Yellowstone has over 60% of the world's geysers. It also has the biggest geyser in the world, that Steamboat geyser that we regularly see erupting just about every week now. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.